Welcome. In today's video, we're going to look at how to derive the maximum likelihood estimate for a continuous uniform distribution. But before we do that, let us first remind ourselves what is the probability density function of a uniform distribution. So, firstly, suppose we have a series of random variables or independently and identically distributed random variables, and they come from a uniform distribution with parameters a and b, a and b being the end points of that distribution. We could say that the PMA or the PDF, the probability density function of xi, is given by this particular function here. And I'll say fx given the parameters ab is equal to 1 over b minus a, noting that xi is an element of a to b, and it would be 0 elsewhere. Now, because it's 0 elsewhere, what I'm going to do is I'm going to actually rewrite this function a little bit differently, and this is going to help us derive the maximum likelihood estimation. And it might not be obvious just yet why, but bear this in mind. What I'm going to do is I'm going to say that that is actually the same. It's the equivalent of b minus a multiplied by what I'm going to call an indicator function, which I'm going to write like this. And this indicator function, I'm going to define it, or a less than b. Basically, what we're going to say is it takes the value 1 if a is less than or equal to, which is less than or equal to b, and the value of 0 elsewhere. And so realistically, that this function here is actually defined for all x an element of R. These two functions here are effectively equivalent, because when xi is not between a and b, this just drops to 0, which is by definition what this drops to in the first place. And we'll see why this particular formation is important in a sec. But for now, let's continue as we normally would. To derive the maximum likelihood estimate, we first need to find the likelihood function. So, going back here, the likelihood function, which I will write as L of A and B, is equal to the product, I equals 1 to n, of all the probability density functions of all I equals 1 to n of all the probability density functions. Sorry, I've just repeated myself there, but it's important to remember that definition. Now, I'm going to substitute in the expression we have above, this one here, into the formula. So this becomes I equals 1 to n over 1 on b minus a, indicator function xi, b, and I'm just going to put this in square brackets to denote that we're multiplying all of those together. Now, we can separate this function because it's the multiplication of two variables. We can actually separate this function into two sets of multiplications. The first set of multiplications is going to look like this. And then the next set of multiplications, I equals 1 to n of I a xi b, is going to look like that. Now, this first expression here is actually independent of the index I, you can notice here. So for this particular case, we're just multiplying this component, 1 over b minus a, n times. So actually what we're just going to be left with is 1 over b minus a to the power of n. This expression here is where it becomes a little bit complicated. So I might go as an aside, I might go to an aside part and just quickly explore this concept of the indicator function. And again, I'm going to rewrite the indicator function, just sort of a definition here, is remember it's something like 1 and 0 if A is true. If the statement A is true, or maybe it might be, let me write it in the same sort of notation. If the statement A is true and B, sorry, not B, let's say A is false. So if we were to look at two indicator functions multiplied together, so say we were to look at indicator function A times indicator function B, what would this come out to be? Well, there are two possible, or there are actually four possible scenarios that could happen. Let's say you've got 1 times 1. That would occur if A is true and B is true. Then you've got 1 times 0 if A is true and B is false. Then you'd have 0 times 1 if A is false but B is true. And finally, you'd have 0 times 0 if A is false and B is false. Now, if we actually summarize this, it turns out that the only time you get a value of 1 is if both A and B are true. So if we were to really look at that now, what we could say is this becomes 1 times, or not even 1 times 1, I'll just say 1 if A is true, B is true, but a 0 elsewhere. Now this is an important fact because actually what this is the equivalent of saying is this is the equivalent of the indicator function if both the statements A and the statement B is true. And this is a fundamental property that what we're going to use in terms of our equation beforehand. So if we go back to the previous page where we had the multiplication of multiple identity functions, what happens here is we now recognize this is the equivalent of an indicator function such that each, let me write it in a nice sort of notation. Let me write it in the right pen, mind you. It means that each A x1 B must be true. It means A intersect x2, A less than or equal to B, or less than or equal to x2, less than or equal to B must be true, all the way up into A less than xn, B is true. Oops, and there's nothing after that, so we can close the bracket. So if this statement here, the product of these indicator functions is just saying that each particular inequality must be true. So what I'll do in the next page is I'm going to simplify that a little bit, and I'm going to say this means that LAB is equal to, again, we've still got that 1 minus BA to the power of n at the front, but we're multiplying this now by an indicator function, and I'm going to use the simplified terminology, which is, the intersection of I equals 1 to n of a xi b. And those are the sort of possible sets. That's just shorthand. This is just a shorthand way of saying basically a shorthand way of writing what we had on the previous page here. It's just the intersection of each of these cases here. Similar to how the expression of the sum works. All right, so we've got that. That seems good enough. Now let's do a bit of thinking here, a little bit of sort of let's say some thinking about exactly what the intersection of all these sets mean. Well, it just means that each xi, or each particular value of xi that we pick, needs to be between a and b. So in this particular instance, this is the equivalent of just simply writing a is less than x1 ... xn ... b. All of the sample points are less than or greater than a but less than b, inclusive. And we can actually further simplify this a little bit, which is nice. And we can say this is equal to, again, 1 on b minus a to the power of n. Multiply. Now, what we're going to use is we're going to use some information about statistics. And this is the equivalent of just saying that the first term, the lowest term, which we usually denote as x subscript 1 with brackets, this is the lowest term in the sample, is greater than a, and it's also the equivalent of saying that the greatest term, which we write as brackets in n, is less than or equal to b. And of course, this inequality has to be true by the definition. The inequality in the middle has to be true based on the definition of what those two components are. And so then we can just rewrite that as an indicator function like this. Or equivalently, we don't even really need the inequality in between. We just can write it like that both of those statements need to be true. And of course, just for clarity, our x1 is defined as the minimum of x1, xn, and our x subscript n is all defined as the maximum of x1, xn, because of course those are the equivalent statements. So, unlike typically where we deal with maximum likelihood estimations and we use derivatives and then we solve those derivatives, set them equal to 0 and find the value of the parameter, in this particular instance, we actually can't do that because the idea here is, well, there's two competing ideas. The thing is, there's nothing to really differentiate. Well, we could differentiate the parameters b and a and try and work something out here. But intuitively, what we can see is that two things must sort of be true here. Statement number one is we actually want to maximize 1 on b minus a to the power of n, which actually is the equivalent of minimizing the b minus a, right? If you want to maximize this expression here, you want to minimize the denominator, what you're dividing by. So in this particular case, we want to minimize that difference there. And two, there's another thing we need to make sure, and that is ensure that this expression here, x1 and xn, is equal to 1. Because if that's not true, then, well, this whole thing just collapses. This whole expression of the likelihood function collapses to 0. Now, in order to do this, the way we actually would do this is sort of intuitive, because you put these two statements together, and what you arrive at this particular notion that the maximum likelihood estimate, and let me do it in a bit of a different pen, A has to be equal to the lowest number, and your value of B has to be equal to the highest number in your sample. Because one, this ensures that the first condition is true, and also it ensures that we are subtracting the lowest possible number in this expression from the highest possible number in this expression. And so these two particular rules, those two particular things being true, make these the maximum likelihood estimators. There was no need to do derivatives. There was no need to solve those derivatives equal to 0. Simply, we needed to come up with a meticulous way of, or a logical way of finding those maximum likelihood estimators based on that expression. So you can see here the what was involved here, and the clarity that we got and how we got to this solution was actually really to do with this concept of the identity function and how we expressed the probability density function of the uniform distribution in this way. Without this new expression, we couldn't have got to this this formulation. Now, keep this in mind. This is a common tactic that you can deal with, or that you might have to deal with when dealing with parameters. Let's say that that have, or probability density functions which are defined, their parameters define the endpoints of the distribution. So this is a common technique in using this identity function.